Hi, it's Michael here from Calix. Apologies about the slight delay. As you can see, I'm having a few technical challenges with the technology here. But that's not going to get in the way of us starting this webinar. So, my name is Michael Wheatland. I'm a Business Development Manager here at Calix. Today, look, I just wanted to have a chat with you about phosphate and how it relates to the big challenges that face us in the future. And also how it relates to the water treatment that's going on, whether it's in a municipal wastewater factory, a municipal wastewater treatment plant, or a food manufacturing plant. But first of all, I wanted to take the time to make sure that you're logged into YouTube, to make sure that you can interact with me as we go through the webinar. I'm very interested to hear your take on the situation and how it affects you, how your companies are tackling it as well. So please take the time to make sure you're signed into YouTube so that we can interact and you can type in the chat. As we go through the presentation today, I'm going to try to make sure that I keep an eye on the chat so that I can respond to any questions as we go through the presentation. So please get involved there and make sure you're logged in. Okay, so I wanted to talk about phosphate and how it relates to sustainability. So let's just jump over into the presentation and we'll go from there. So, phosphate. I wanted to talk about sustainability, the phosphate cycle and how that works, and also phosphate removal within wastewater treatment processes, and how ActiMag can help with that. So let's jump right in. The United Nations a few years ago created the Sustainable Development Goals. To give you a bit of context, these are the goals that are agreed by all the countries across the world to be what we want to achieve by the year 2030. The reason I'm having a look at this is because the phosphate cycle and the reasons or the methods that we tackle phosphate within wastewater has a direct impact on these sustainability goals, these sustainable development goals, and the overall sustainability of our society moving forward. So what Calix did was we took a look at these sustainable development goals, and we assessed within our organisation which ones apply to the work we do and how we can further our work to increase our impact on these sustainable development goals. I'd be very interested to find out whether your organisations have had a look at these sustainable development goals and whether they're working that into their business plan. I know that water authorities are some of the most forward-thinking organisations, and I know that quite a few around Victoria and New South Wales and Queensland have taken a look at these goals and really tried to identify where they can improve their local communities and what goals they can have an impact on to result in a much better world after the year 2030. So, as I said, Calix took a look at these goals, and we've identified a number of goals that we can directly affect with some of our products. Zero hunger, so we've created products which are alternatives to using pesticides and fungicides on crops. It's called Booster Mag, so that can be applied to crops throughout the world to boost yield and control pests and that type of thing. Clean water and sanitation, as you would know, Calix is the best, and I'll say the best, magnesium hydroxide supplier in Australia. We've got a reputation as having really high quality products, and that directly impacts clean water and sanitation through odour control, through corrosion control within the network. That applies to this sustainable industry and infrastructure goal as well over here, number 9. So the reduction in hydrogen sulfide reduces the corrosion in the network as well. We've also got efforts to improve affordable and clean energy. So I'm not sure whether you've heard about it, but Calix has got some using our high surface area products to get into the battery manufacturing game, and start looking at manufacturing batteries here in conjunction with Deakin University. Climate action, so all of our products are created through our Calix flash calciner, which can capture carbon dioxide, and we've got a couple of big projects over in Europe that are designed to capture the carbon coming out of cement plants. We also do an aquaculture product, so looking at life below water, and the partnership goals. So we often partner with universities and that. So look, I'd be interested, if you want to take the time and type in chat, I'm very interested to find out how your organisation is tackling these sustainable development goals, and how you're actually applying it to your work. How does that relate to phosphate though? So let's talk about the great challenges that are facing our society in the coming years. So one of the challenges that we face is climate change. It's fairly easy to see. You've all seen the hockey stick graph. So it's around long-term stable temperatures, and then it shoots up when the Industrial Revolution comes along. This is also related to how we deal with phosphate, so I'll come to that in a second. Another challenge that you'll be incredibly familiar with right at the moment is this emerging diseases, and specifically COVID-19. So what I found was this flattening the curve idea is very helpful to be able to understand the coming challenges, that these global challenges that we see moving forward. COVID-19, it's been a fantastic response. This idea of flattening the curve has allowed us to visually represent the direct impact on humans by taking action that is well researched and understood by scientists. So as you can see, if we do nothing, the amount of human suffering will be quite high. But with action, locking down society, staying at home, and all that type of thing, we can flatten that curve and reduce the amount of human suffering. So if we look further out in the future, we can potentially use this idea of that curve to look at future challenges. So the one that's obvious is climate change. So if we don't take action, we're not going to be flattening this curve. This climate change is one of the big existential threats facing society, but with action, we can do exactly the same thing as what we did with COVID-19, with the disease. We can flatten that curve and reduce the amount of human suffering. So looking forward, as you can see with climate action, it's no climate action. It's quite a bit of a problem, but we can flatten that curve with action. Beyond that, there are certainly other challenges that are going to be facing society in terms of sustainability, and one of those challenges is actually phosphorus. Phosphorus is not a renewable resource. It is a renewable resource on the geological timescales, but it's not a renewable resource on the timescales of our lives. So it's worth having a bit of a look at this, and the experts believe that within 300 years or so, we'll be looking at this phosphorus shortage. So it's a good idea to look at what we're doing right now and how that's going to impact that curve, and to see whether we can flatten that to, again, reduce the amount of human suffering in the future. So let's have a quick chat about the actual phosphorus cycle. So as you can see, the phosphorus cycle, it's quite simple. Phosphorus is in rocks, as just natural rocks that get pushed up from the sediment under the ocean and in waters. So sedimented solids that have gone into water bodies and been pushed up into mountains. Those rocks erode and they put phosphorus into the soil. The soil is then used by plants and animals to grow, and the phosphorus becomes soluble, and run off into waterways, so streams and rivers, and eventually ends up in the ocean as undersea sediment. That phosphorus in a phosphate form then goes back into sediment rocks, and it eventually, on a timescale over millions of years, gets pushed up into mountains and rocks again. So as you can see, this phosphorus cycle is very slow, and that has directly impacted on society in the past. So there's a thing called a Malthusian trap, where society, the population of society would grow up until the point where food shortages became a problem. So as you can see, the world population kept fluctuating up and down at around the 1 billion person mark for many thousands of years, probably forever. This limit was really a function of the amount of nutrients that are in the soil. So they were able to get enough food, and then the population would increase, and all of a sudden, there's not enough food, and it would come down again. But come the Industrial Revolution, that all changed, and as you can see on the picture on the right there, phosphate farming was phosphate mining was played a significant role in that change. So there's a great divergence in terms of the population, and that was related to the creation of agriculture and modern fertilisers. And phosphorus plays a big role in that. So effectively what we're doing is within the phosphate cycle, we've taken that natural phosphate cycle and we've introduced a new stream where we take phosphorus that's in rocks and mined out of phosphorus deposits, phosphate deposits. We then use electric arc furnaces to convert that phosphorus into usable fertiliser, phosphates or superphosphates, and we apply those fertilisers to our modern agricultural crops. That results in significant runoff and discharge. So the discharge can be from either from farms where they've applied fertiliser and it's running off the soil, or as you would imagine, those crops, they take up the phosphorus, we eat them, and that goes into the municipal wastewater system, and that ends up pretty much in the ocean. So whether it's treated, and the phosphorus or phosphate is able to flow often with the effluent into the ocean, which effectively creates a new cycle within this phosphorus cycle. So as you can see, we've shortcut this cycle where the step of erosion to remove the phosphorus from the rocks out to the soil to a something that's usable within plants. It takes a long time, so we've shortcut that. But the return from undersea sediment back to being rocks that can erode takes a long time. It takes millennia. So what we're effectively doing is we're speeding up part of this, a significant part of this phosphorus cycle from stored phosphorus within the rocks and putting it back into undersea sediment. As you can imagine, this might be a bit of a problem moving forward. So as I said, the experts think that we might hit a bit of a limit with this within about 300 years or so. All right. So the phosphorus cycle, but like how does that relate to what we're doing and human life? So phosphorus and phosphate plays an incredibly important role in all growth, in all life. So DNA, the backbone of DNA, is actually phosphorus, as you can see along the double helix of the DNA chain. The thing that joins up all of the DNA is actually phosphorus, and that is taken up in terms of phosphate, that is the fertilizer in the soil to create that DNA. So it really is the basis for all of our modern agriculture and the the fantastic fruit and vegetables that and the abundance that we see today. As I said, if you're keen, get involved in the chat. I haven't seen any comments come in yet, but if you're interested or you've got any comments, please jump in there and let me know. So just moving forward there. Okay, so we've learned about the phosphorus cycle, the phosphate cycle. That really doesn't apply to wastewater, does it? So within the wastewater industry, you might be quite familiar with how phosphorus forms or the problems that it causes. Some people see phosphate as this just a plain phosphorus rock, a phosphate rock. Often people associate phosphorus with a scale which is formed within pipes known as struvite. So this can be a major problem on the discharge where you've put it through an anaerobic digester and you've got a fair bit of phosphorus in the wastewater. It can deposit on whether it's pump impellers or the pipes on the discharge side. It can certainly reduce the pumping capacity and efficiency of the discharge process. And finally, the other big problem that phosphorus can create is algal blooms. If we just allow the phosphorus to be discharged with the wastewater effluent into waterways or into the ocean, that additional nutrient can encourage the algae, the blue-green algae, or other types of algae to grow really rapidly within waterways. That creates an algal bloom, which then consumes the oxygen within the water. And when those algae die, it can cause some pretty serious consequences for fish kills and things like that. So the control of phosphorus and phosphate within the wastewater industry is quite important for our waterways and overall sustainability of the whole world, really. So how do we deal with that? Traditionally, there's been really just one way, which is chemical phosphate capture. Alum is often used, or aluminium sulfate. It's a commodity grade product which is used to capture the phosphorus. So as you can see here, we've got alum, which is the aluminium sulfate tetrahydrate. That is reacted with the phosphorus and it creates a aluminium phosphate. This product, the aluminium phosphate, it forms within the sediment, so it can settle out within the sludge of wastewater systems, but it's also quite toxic because aluminium is a heavy metal along with iron and a lot of the other mineral or metal products that are used to form salts to deposit this or take the phosphate out of the system. What does this result in? So often it results in heavy metals getting into the food chain or the water cycle that we really don't want them to be there. So as you can see here, there's an article from the newspaper which is showing and it's just recently as well, so December 2019. It shows the problems that can occur when you end up getting metallic sludge in drinking water supplies. This can, it can be iron, it can be aluminium. It's a bit of a problem. So in terms of managing what happens to that sludge after you form the aluminium phosphate or the metal salt is very important because if you put it in the wrong place, it can end up in the food supply. So that's what's happened in the past. But what's the alternative? So this is where Calix really takes a step up. How is ActiMag different? So ActiMag is a magnesium hydroxide product. Magnesium is quite different to aluminium and iron in the food chain. Magnesium is seen as a nutrient. There doesn't seem to be any upper limit in terms of toxicity. So the amount of the amount of magnesium that you put into fertilizers and things like that. It could be in sludge, and the sludge is composted and then put onto whether it's crops, or it could be put onto the land to allow more plants to grow. There's some fantastic benefits there in terms of using a magnesium as an alternative to other metals, in terms of capturing that phosphorus or the phosphate within the sludge. So that way the sludge remains usable afterwards. ActiMag, however, has an additional benefit in that ActiMag uses what's called the interstitial space, or the pores within the particle. ActiMag is a really high surface area product, the magnesium hydroxide. The way we produce it is quite different to commodity grade magnesium hydroxide. Magnesium oxides and hydroxide are traditionally made using taking a large rock, passing it through a big kiln which heats the whole thing up, and it overcooks it, and it ends up melting all the surfaces, so that it becomes essentially an enclosed space. So it's just a round particle. The ActiMag's quite different, because we take the material, we grind it up so that it's really fine, down to about 45 micron, and then we sift it to make sure that we've got a nice particle size distribution, and we flash heat that. So we heat it up to temperatures well above 800 degrees, and that occurs only for like 20 seconds or so. So what happens is the magnesium hydroxide forms. So magnesium oxide forms from the magnesium carbonate, and as it emits the gases from within the particle, it leaves a whole heap of these pores. As you can see, this is a scanning electron microscope photo of one of our particles, and it's full of crevices and cracks. So what can happen is the phosphorus can actually get inside this particle, and it forms what's known as a struvite. You might be familiar with that from the scale, because the phosphorus scale that forms on the edges of pipes, that's also struvite. But the difference here is that the struvite can form actually inside the particle, so it doesn't end up on the pipe. These particles of ActiMag, the high surface area magnesium hydroxide, it allows the phosphorus to come inside the particle, and it deposits the phosphate within the particle. That particle is then discharged with the solid stream, so the sludge stream, which can then be composted. And because of the beneficial nature of the magnesium nutrient, you can use that sludge on flowering plants or other applications where you're growing things to encourage growth and improve crop yield. Looks like we've got a question in here. So Emma, I think it is. Is the product only usable for wastewater, or on treating lakes as well? Yes, yeah, absolutely. So we have spent a little bit of time looking at lakes, especially in Asia, and a couple of ornamental lakes in Australia, I believe, a little while ago. So yeah, absolutely. The product can be used within freshwater lakes. Often it'll actually capture the iron as well and settle that down to the bottom. So you end up getting a clarifying action within the freshwater lake as well. We've got a product called Aqua Cal Plus, which is used in aquaculture, where we apply the product to fish farms, prawn farms as well, where it's designed to reduce the amount of iron and phosphorus and all the heavy metals that normally contaminate the water, just due to the excrement of the fish and the prawns and that, and it settles down into the sludge. That way, they're not consuming it, and they don't take up the heavy metals within the food chain. You end up having a higher yield of the aquaculture animals, so fish or prawns, and you end up with much cleaner lake. So yeah, absolutely, it can be used for treating lakes as well. But that's looking at this high surface area picture on the side here. Really, this is how the action to how it removes phosphorus. So it doesn't require the entire bulk pH to change. The pores within the particle have an internal raised pH, and that allows the formation of that struvite crystal actually within the particle. And again, that's discharged with the sludge and doesn't carry on with the effluent within wastewater treatment. So that way, we're removing the phosphorus or the phosphate within the effluent stream, and we're storing it within the sludge. How do we apply it to systems? So phosphate is captured essentially just by dosing ActiMag as you would within a sewer network for odour control, but it's dosed into the head of a wastewater treatment plant. It can be anaerobic or aerobic, it doesn't really matter. And as I said, the bulk pH has less of an effect on it because of the high surface area particle. So we capture it in the phosphate in the sludge. It remains available to plants, so that struvite crystal is actually is soluble and can be taken up by plants that are growing in that soil after you've composted the sludge. So that's one of the strong benefits in that it's non-toxic. It can be used in the food chain as long as your sludge complies in other ways in terms of the grade of sludge that you're putting out, and you don't end up with toxic heavy metals in the sludge. In terms of how it's also used in the wastewater industry, ActiMag is used for the odour control and also corrosion control to reduce hydrogen sulfide within the wastewater network. So if you're trying to capture phosphate within your treatment plant downstream, what you can do is you can apply it upstream for odour control and end up capturing a bit of that phosphate as it's coming into the treatment plant within the sludge. That way you don't need to use as much alum or ferric chloride within the treatment plant, and it certainly has benefits in terms of pH and alkalinity control for wastewater treatment as well. So how do we apply it? We've got dosing units that we put in place. We can do analysis of hydrogen sulfide and phosphates within wastewater treatment systems. Calix also offers full service delivery, so we produce the material here in Australia. We've got our own supply chain, so we deliver the product with our own people, and we can provide service and maintenance on an ongoing basis. So how does that relate to the phosphate cycle? Or the phosphorus cycle. So bringing it right back to where we started. This phosphorus cycle, as you can see, there's this new chain that's been created with the invention of this phosphate extraction process from rocks. What we want to do is we really want to flatten that curve in terms of the shortage, the phosphate shortage that we might see in a few hundred years' time. So by doing this, by capturing the phosphorus within a form that's usable within the food system and able to be taken up by plants and having no toxic heavy metals within the system, we've created this new loop. So this ActiMag capture takes the phosphorus within the runoff and discharge, and it allows us to return that phosphorus or the phosphate in the form of phosphate back to the agricultural system. So effectively all of this phosphorus that is going to be running off and trapped within undersea sediments, eventually trapped within undersea sediments, or potentially locked up within soils that are heavy metal contaminated, if you're using, say, an alum or a ferric to capture it. We're effectively shortcutting that problem, and we're taking the phosphorus and we're returning it creating this new loop within the phosphorus cycle and returning it to the agricultural process. So that's how we've ended up where we are in terms of phosphate capture, and the result is an incredibly sustainable solution moving forward in terms of grabbing that phosphate and reusing it, which is incredibly important for what is effectively a non-renewable resource in terms of the timeframes that we're looking at. I'd like to just have a look at the questions now. Let's have a look. What is the AS to follow? I assume by AS, apple juice. Hi, apple juice. I assume by AS you mean Australian standard. So this is a fairly new process. So there is no direct Australian standard that to follow in terms of capturing phosphate, but effectively what we can do is we can come in. Calix has the engineering capability to come into any wastewater treatment process and have a look at the system that you're looking at, have a look at the system that you're running, and figure out the best way to apply the ActiMag in order to capture that phosphate within your process. Let me just flick back so you can see me properly. So we obviously follow Australian standards for designing the dosing units that go into the wastewater treatment plants in order to deliver the magnesium hydroxide or the ActiMag into the system. But as I said, there's no direct Australian standard for phosphate capture. But there are significant benefits for capturing that phosphorus in the form of struvite within the sludge, because, as I said, that could be reused within the phosphorus cycle, and it doesn't end up in the sediment. Just wondering if there's any more questions. I'm not seeing anything coming in. No, having a look down here. No, it doesn't look like any more questions. Okay. Look, thank you very much for taking the time to join the presentation today. If you've got any more questions, please drop them in the chat, and we'll certainly have a bit of a look at responding to you directly if we didn't get to. I think I've covered all the questions, but if I haven't answered any of your questions, or you can add a comment after the video's ended, so just down in the comments below, and I'll certainly make an effort to get back to you and have a chat about your specific process. There's certainly ways that Calix can provide this solution for capturing phosphate and phosphorus in a sustainable way, to whether it's your water authority or food manufacturing plant, and that way you can address the sustainability of your process, as well as improving those sustainable development goals that we talked about at the start from the United Nations. So, look, thank you very much for your time. Just quickly before you go, a little reminder that oh, sorry, there was a little bit that I missed here. So phosphate removal. So as you can see, sorry, I should have done this earlier. So phosphate removal can be done within treatment plants. So this is a case study from Central Victoria at an abattoir. As you can see, it's a fairly linear capture in terms of the phosphorus with the amount of ActiMag that's added. So as you can see, it's quite predictable. So in terms of quoting, in terms of getting you a quote and being able to estimate how much ActiMag we would need to use in order to capture the phosphate, it's very predictable. There are other plants that we've captured phosphate on. So as you can see with our lab testing, the amount of ActiMag that you would use compared to something like a ferric chloride or alum is significantly less, and it's got the additional benefits in that you don't need to. It's much better for alkalinity control and pH control. Calix is able to provide solutions for essentially any size or any location. So we've got an engineering team that designs these dosing units that can be put in place at essentially any location. big and small as well. And we also provide service and delivery. I did kind of mention that quickly before, but if in this period where we often don't want people interacting with essential workers, we can provide all of the servicing and maintenance required for the dosing systems that deliver the ActiMag into the wastewater systems. All of the products are ISO 9001 quality certified, and we're safety certified as a company as well. Just quickly, we do have a strong security of supply within Calix. We own our own mine over in South Australia, so all of the rock we mine out of there. We bring it over to Victoria. It's processed through our flash calciner. So as you can see here, the flash calciner is based down in Bacchus Marsh in Victoria, and we also have vertical integration out to being able to deliver that product into wastewater treatment plants, also wastewater collection networks, sewers, and also food manufacturing factories and abattoirs. Abattoirs is a particularly interesting one because the amount of phosphorus and phosphate that's in blood runoff from the abattoirs is much higher than most other industries, as well as the amount of phosphorus that's in the wastewater from canneries and frozen foods can also be quite high. So being able to having confidence that all of our products are supplied locally, our supply chain is local, we're not impacted by the international restrictions and that are going on at the moment is quite important in terms of confidence around those essential services, being able to provide wastewater services and also food. Don't forget, in the next few weeks we've got a couple more webinars coming up. Next week I've got a bit of a special treat for everyone. We've got a discussion with an international expert, Doug Kelly. He's the CEO and founder of IER, which is a company in the US that specialises in magnesium hydroxide and its a chemical application for odour control, for pH control, for alkalinity control. So that interview with Doug Kelly will be the same time next week, next Thursday at 10 o'clock. And also in the coming months, we're going to be presenting weekly webinars to hopefully give you a little bit of kill that boredom while we're all stuck at home, but also to improve your professional development and demonstrate, so you can demonstrate to your workplace that you're putting in the time and the effort, and you're attending webinars and doing a lot of learning while everyone's stuck at home. So, look, thank you very much for joining me today. Sorry about the technical difficulties that have occurred at the start of the webinar. I think it was related to an upgrade that YouTube made, but I'll make sure that it doesn't happen next week. I appreciate your time, and please don't forget to comment and ask some questions. If you've got any other questions, we'll get in touch, and we'll find out a way for you to be able to interact with, for you to be able to apply this within your system. There is another question that's come in. Sorry, Emma. Is Phoslock a competitor? Probably not. Phosphlock it's a commodity grade magnesium hydroxide. We have compared the two within the laboratory, and the high surface area of the ActiMag has a significant impact on the capture of the phosphate. So as I said, just going back to one of my previous slides here, I'll just flick back to it. So just flicking back to this slide, as I mentioned, commodity grade magnesium products like Phoslock or other types of those products, they're produced in quite a different way, and they end up with a very low surface area. So I know commodity grade magnesium hydroxides that we've tested can be as low as 40 square metres per gram, whereas the ActiMag, it's been produced, the magnesium oxide we produce can have a surface area that's well over 300 to 350 square metres per gram. So the mechanism for capturing that, the struvite, capturing the phosphate particle, like actually inside the particle, is quite important for making sure that it doesn't deposit on pipes and things like that, and you can capture it in the sludge and it gets discharged with the sludge. So the high surface area of the ActiMag is very important when it comes to capturing phosphate. All right, looks like that's the last question of the day. So as I said, thank you very much for joining me. I really hope you join me next week for the discussion with Doug Kelly. It's going to be a really good one. It's a little bit more fundamental chemistry, but it certainly gives you a really good idea of how pH is controlled and how it relates to alkalinity. And it's a really good discussion with Doug, who's clearly an expert in the field. It's going to give us a really good perspective of what they're doing in the United States as well, in terms of cutting edge technology over there, and how they're using the magnesium hydroxide within wastewater treatment and other systems to control pH and alkalinity, and how it's significantly better than other solutions like caustic soda or lime and other things like that. So I'd love for you to join me next week. I promise there's not going to be any more technical difficulties, and thank you very much for joining me today.
Calix was founded in 2005 by myself and a Queenslander named Colin Hawley. He had a great idea for a new type of kiln or furnace. As Connor and I developed the idea, it became apparent that the technology had the potential to be applied to many industries and could help address some of the world's most pressing problems. We raised some money, did some small-scale testing, and it gave some great results, encouraged us to build a commercial-scale facility at Bacchus Marsh in Victoria. The Calix flash calciner, or CFC process, involves grinding minerals or other feedstocks to between 1/100th and 1,000th of a millimetre in size, then flash heating them in an externally heated reactor in a very short time, up to about 950 degrees centigrade. As trapped gases in the material bubble out through the particles, they create highly porous structures. These particles are then cooled very quickly, leaving a very porous, honeycomb-like structure. New materials produced by the CFC are proven to have similar reactive properties to nanoparticles, without the safety concerns and high costs, but with all the benefits that nanotechnology is developing into numerous products, applications and markets.
I joined Calix in 2013 because I could sense the huge potential of this technology. It's a platform technology that has two sides: production of nanoactive materials on the one hand, and the potential to be applied in CO2 capture on the other. Our first commercial product was released in 2013 for wastewater treatment, followed closely by two more products in 2014, one for infrastructure protection and a specialty chemical additive. All these products are now in export. In addition to our commercial products, we also have some pre-commercial products already in paid trials in Asia and Europe that look really exciting. One's a water conditioner to help with yields and environmental problems in aquaculture. And the other's a non-toxic, environmentally friendly, broad-spectrum crop protection product. We also have a rich research and development pipeline with some really exciting developments in advanced batteries as well as CO2 capture for the lime and cement industries.
Additionally, if the materials have trapped CO2, the technology can separate that CO2 directly for no additional energy penalty. For example, limestone by weight is approximately 50% CO2, which is released as a gas when making lime, and is therefore why the cement and lime industries are very CO2 intensive. Application of the technology in CO2 mitigation is thus of interest to those industries.
And we're piloting these programs with over 25 million in funding from Australian and European governments. And we are working with some of the world's largest companies in these areas. Having proven its commercial products and business models, Calix is about to embark on some serious market entries into the US, Europe and Asia to grow its revenues and margins. We will also continue to develop our pre-commercial products into fully fledged commercial products and processes through both direct and distribution sales and licensing strategies. And lastly, we'll continue to develop the multitude of high potential R&D applications into some of the world's fastest growing industries. Calix really is all about creating new materials and processes to solve global challenges.